Hello, Darrell Berry Jr. back with some more problem solving. So we'll continue from where we left off and solve some more thermodynamics problems. I read through the remaining two sections of the book, at least the subsections to finish that section. Let's see what we have in the way of problems at the moment. So we have this one I was about to start on, problem 6.5 here in the previous subsection, dealing with the partition function, which is z. Right, so imagine a particle that can be in only three states. So I'll call these states S1, S2, and S3. Negative 0.5 electron volts, 0 electron volts, and 0.05 electron volts. This particle is in equilibrium with a reservoir. So T R equals 300K. Calculate the partition function for this particle. So Z should equal sum all the states Boltzmann factors, which in this case will be E negative E S1 over KT plus E negative E S2 over KT plus E to the negative E S3 divided by KT. So this should be E to the 0.05 electron volts divided by KT plus E to the 0 plus E to the negative 0.05 electron volts divided by KT. So if we have K equals it was 1.381. Let me scroll to the uh, constants. So there was a table in here. I want to look in here to save from loading my formula sheet, but I may need to just load my formula sheet. Surprised this is not in some kind of formula sheet here, but this actually saved me some time. because we can see that Boltzmann constant in one form is 8.62 times 10 to the negative 5 electron volts over K. And in our problem, K is 300. This T is 300. So that means KT is exactly what's in this book, which is 8.62 10 to the negative 5 electron volts over K times 300K, which is 0.026 electron volts, which is about 1 over 40 electron volts. And this is the one I was thinking about before, 1.381 times 10 to the negative 3 joules over K. I need to put these full formulas on my formula sheet. Check the stream, make sure everything is fine. Everything seems good. I'm not sure why the what's column is showing offline. Okay, there we go. That also equals 1.381 times 10 to the negative 23 times 300, 4.14 times 10 to the negative 21 joules. All right, let's go back to our problem. All right, so we're calculating the partition function. So we have that. So we have, that's going to equal E to the 0.05 electron volts divided by 0.026 electron volts plus 1 plus 1 divided by E to the 0.05 electron volts divided by 0.026 electron volts. So let's see what this equals. Have E 0.05 divided by 0.0026. Wow, that's a huge number. So we have 224,810,690.6 plus 1 plus the inverse of that, 0.45 times 10 to the negative 9. So that equals 224,810,691.6. Right. So let me check and see if I can confirm about this answer. Okay, I typed in an extra zero. That's what I did. That will do it. Yep, it is high, Galva. I typed in an extra zero. That's extremely high. Good to see you, by the way. Let me know if you have any questions, any other errors you see. Thanks for letting me know. So 6.84 plus 1 plus the inverse of this, 1 divided by that, 0.14. Right, so this seems better. 6 point something plus 1 plus that. So we have 6.99, which is about 7. All right. What do you think? What do you think, Galva? Seems better? Seems reasonable, I would say. What does it say next? It says calculate the probability for this particle to be in each of the 3 states. Let's see here. So we saw earlier from our derivation that the probability is this. I should probably convert this into a, we haven't already. Did I convert this? Yes, I did. Right here. Definitely have to put this on the formula sheet. So that's the probability. And Z we calculated earlier. And let me make sure to put that in a, didn't I do a derivation for that? I thought I did. Maybe I just did not note it. It's in a different file. So let me convert it here. Right? Z equals E. Let me confirm that that's correct. That copied over properly. Previous answer should be around 8. In the world. Oh my gosh, I typed 0 for the, instead of 1. Thanks. So that's 7.99. About 8. Awesome. That clarifies that. So that's typo errors in my calculator. That is correct. Good catch, Galva. Let's see about this V. I have the very good. So this is conversion, right? Sometimes this conversion changes the something around. Z equals the sum S E negative ES. I notice that they have a lowercase s for state, not for entropy. So used to have a capital S. So Z, which is the partition function, is the sum of all the state S's over KT, which is the sum of all the Boltzmann factors. Perhaps I'll add that equals. And by the way, Belva, like in what, middle of May, I'll have a reveal on where I'm going for graduate school. So look out for that one. Boltzmann factors, another slash there. Did I put the wrong slash? Is it that one? Yes, that one. All right. We have Z equals to some state of E of the exponential energy of that state, negative, divided by KT, which is the sum of all the Boltzmann factors. So I try to be more proactive on my formula sheet, even though it is good to go over the formula sheet like right before the exam, like helps for a review. But the majority of my formula sheet, I think, will be pretty much the same before the final. So I'll try to see if I can add these few things more succinctly. All right, so that's that. Now we want to get the probability of each of these states, it says. So the probability of S1 is going to be 1 over Z e to the negative the energy of S1 divided by HC. Lose this extra negative. So that's going to be 1 over 8. I'll just use the rounding. E to the negative, and the energy of state 1 they gave us. Technically, I guess this should be E S1, E S2, E S3. So it should be that. Negative, each E of S1 is negative, so that's going to be positive 0.05 electron volts divided by KT, which, didn't I calculate that already? I did. So that's going to be 1 over 8 times 6.84. So that's going to be what? 0.855. So the probability of state 2 of this, what is this particle? Again, a particle. It just didn't state what kind of particle. The probability of this particle having the energy of state 2 is 1 over Z times E to the negative the energy of state 2 divided by KT. So this is going to be 1 over Z times e to the 0, which is 1 over 8 times 1, which is just 1 over 8. So that's going to be 0.125. And the probability of the particle to be in state 3 is 1 over Z times e to the negative the ng of state 3 divided by KT, which I've also calculated, which is 1 over 8 times 0.14, which is equaling, and I'll use the actual number rather than the one I rounded off. This is 0.01. Technically, I should increase this up since I rounded that one down. So technically, it should be 0.19, if I'm thinking of that properly. So we know that all of these probabilities should add to 1. So 1. Hey, what's going on, Catherine? How you doing? So doing some thermodynamics problems for chapter 6, section 1 of our thermodynamics book. I was going to do an overview of these, but since you're here, you could see this part here. And tonight in the science hour on the other channel, I'll just go to section 6.2. So I think I'll do it that way, so you don't have to see the repeat. So 6.2 will start with average values. So I'll start with that one tonight. Still review it beforehand, so I can give you all a good flow. Right now I'm on 6 point what again? Oh, awesome, Catherine. Let me give you a link here. There we go. Awesome. Thanks, Catherine. Appreciate it. So there we go. So just to test this, the probabilities should all add to 1. So that should be the probability I of SI. So that should be 0.855 plus 0.125 plus 0.019. So, and I'll just add up my rounded values, 0.855 plus 0.125, oh, 125 plus 0.019 equals about 1, 0.999, given some rounding. All right, so everything adds up. So this seems to be the right answer. Oh, this is my other channel, Catherine. That's why you didn't have a wrench here. So this is my STEM channel. So I have a personal channel where I talk about all kind of stuff, even though lately it's been mostly STEM because I've been focusing on my schoolwork and stuff. Some on my other channel, sometimes I do metaphysical stuff or current events or what have you. But this one is my STEM channel where I focus only on STEM, and I go more in depth, I would say, on this channel. So on this channel, I would say I may talk about things in more detail than I would on the other channel, and I might do like I'm doing now and actually work out problems. So here I'm like actually working out the problems live. I would say the other channel is more like an overview, and there's more entertainment value, where here is more just scientific rigor, I would say. That's what's going on with that. But still, the link is the same for the Patreon, and the link is the same for the website. But if you go to the main website, you'll see there's a channel for each one. So like there's like a STEM channel link, a personal channel link, and a next entity channel link. Yeah, so that's all it was. So I haven't been on this channel in a while, so that's probably why you haven't seen me here. but I'm gonna start being more consistent because I noticed somebody that actually joined the Discord and was saying, "Hey, you did a video on linear algebra a while back, and it really helped me." So I was like, "Oh, okay, so some people are watching and they get some help on this channel, seeing me go through the problems and things like that." So that motivated me to come back on this channel and do some more rigorous stuff as well. So I'll be seeing me more often. So we have that, and this was just a test. And the last thing on this problem, part C. Okay, let's see what they're talking about. Hopefully you're not getting too extra on this one. It says because the 0 point for measuring energies is arbitrary, we could just as well say that the energies of the three states are 0, 0.05, and 0.10 electron volts, respectively. Repeat parts A and B using these numbers and explain what changes and what doesn't. Okay, yeah. They're not being too extra, but. So let's see what we have here. Okay, I'll just do what they say and go through the whole thing. So, and I'll see if I can spare some time by copy pasting some stuff. So, and I'll do everything a different color to help highlight the change. So now the energy of state 1 is going to be 0. I noticed they're very good about calling the ground state energy of the electron, the hydrogen atom, 0. Like my quantum professor, who I also had for modern lab, he drills into our head that the uh, uh, ground level energy for a hydrogen atom is negative 13.6 electron volts. And he's a longtime professor. Believe he does experimental quantum. I don't remember what he does, actually. I don't remember what he does. I know he's prominent in the modern lab. Like he helped build the modern lab. But he's one of the professors who is on the stage when you walk for your diploma. And what he says is, and I believe him. Of course, I don't believe him about turning you back. But he says that when he gives you your diploma or he shakes your hand, he asks you, "What's the rest energy for a hydrogen atom?" And if you don't give him the right answer, he sends you back. Like he turns you around, and you can't graduate now. You got to go back for another semester. So he doesn't really turn you around, but I'm sure he does ask you. But he asks us this so often that everybody knows it. So, and he talks about how people, they tell him 13.6, then he lets them go. Uh, but I noticed that they're good about doing 0 for the ground state, and I guess because they do this shift thing, right? But that's just an aside. So let's keep on going. So then we have 0, then another 0.5, 0.05, and then 0.1. So these are the energies that we're working with. And maybe I should just actually work through this thing so I can get some practice. So calculate the partition function. We have z equals, and I will go ahead and copy the function down. So z equals this. That's the partition function, the sum of all Boltzmann factors. So z equals e negative e s1. And I keep wanting to make this a capital because I'm so used to doing entropy over the last few months. Plus e negative e s2 over kt plus e negative e s3 over kt. So this is e to the 0 plus e negative 0.05 over kt. And we already did kt earlier. I'll just write that in. Kt was 0.026. I just can't write an extra 0. So it messed me up earlier when I was doing the first calculation. It was 10.026 electron volts plus negative zero point 0.1 divided by 0.026. This S is actually for the energy of the state. So I know the terminology gets confusing, and we talk about that in thermal because one day last week he brought in more stuff. Like I'm behind because I focused on the exam, the third exam. So all of this stuff is stuff technically we covered a few weeks ago. So technically the class is like on chapter 7, but whenever I'm in a class and I have an exam coming, I just focus on the exam and I kind of like ignore the other stuff. Except I have to do the homework a bit, but this homework didn't come beforehand, so I ignored it. But as we go along, when we go to chapter 7, he introduced another S and like another T, and people's like, what? And it's like, kind of like you have to understand through the context of the problem what the S is. So in this context, since we're talking about E, the energy, and we're talking about a particle, this S will necessarily be the state of the particle. So let's say the particle has these states, and this would be the ground state, and this would be the first excited state, and this would be the second excited state. So in this case, we're saying the first excited state, the energy is 0, at least the ground state. The next excited state will be 0.5, and then the next will be 0.1, 0.05 is what we're saying. And I'm going to be confused myself about the energy states because uh, like normally it starts negative, like I was saying before, it would be negative 13.6, and then it'll be negative, I don't know, 0. Uh, negative 5, let's say, or whatever it'll be, and then negative 1, let's say. But these are the energies of the electrons, and they're just that each state will have so many different degeneracies. Like you might have only one with this energy, but you might have 1, 2, 3, 4, 5 with this energy, and you might have 10 with this energy as you go up. And the degeneracies, like how many different states have that same energy, S, will determine the probability. Oh no, yes, but S does work with that. Yeah, it gets confusing, right? But like you said, it clarifies. You should think of the context, then it makes a bit more sense. But context is key, and they do mean that because in the problems they just give you a little something, and you have to look at the context to understand. Which is why I was worried about this quantum 2 exam. I'm pretty sure I didn't do too well. I'm just focusing on the final, so the final will replace the lowest grade. So I was just going to skip it, but professor was like, I communicate with my professor, let me know, hey, you said that if we miss this exam, the final, if we miss one, the final is boosted up to cover the points. So I think about just missing it. And he was like, don't miss it, it'll help you prepare for the final. And I was like, so you're saying that the grade for the final will replace the lower? He was like, yeah. So, I'm sure I can do better on the final because for one, most of it is not that last section. And if it is, I could just focus on it more. I did really well on the first exam. I got an 89. So I'm pretty sure I'll do well in the final. So I'm just focusing on the final for that. We will get to that. I may talk about that. Uh, I'll talk about some of that next week, by the way, because I scheduled that quantum talk for you for next week. So we have 1 plus. I'm pretty sure I calculated this one earlier. This is the same value for that. So yeah. So this is about 6.8. Nope, actually, hold up. It's negative. So it'd be the 0.141. So it's negative. So this is 0.14. So again, all I did was recognize that this is this. That's the same thing. So it's this right here. It's the same thing. And this one is the only one that we didn't calculate because they wanted us to point out what changed and what didn't change. So now I have to actually type this one in because it's different. I'll just find what I did before and type it in instead. I'm gonna make sure I didn't make a typo somewhere. Yep, yep, that looks good. So I'm going to type 10. So this ends up being 1 over 46.81. Yep, it was good. And yeah, I was proud of that myself. I mean, it's not an easy class. But he's a good professor. He makes things very clear. All right. So we have 1 plus 0.14. I'll actually copy the actual value down plus that. So that equals 0.18888. I'm going to be pedantic with it. There's a 0 after that. So this is what z equals. All right, so let's look at the probabilities and see if this changes. So calculate the probability for the particle to be in each state. So the probability of S1 is going to be, now I'll just copy this down for convenience. And I'll close up after I finish this problem. Yeah, about 40, 45 minutes. So I'll wrap up after this problem here. That's a probability 1 over z. So that's 1 over 0.188 times e to the, so I'm doing the energy of state 1. So that's e to the 0. So that's going to be 1 over, I can just calculate that. 1 divided by z. So this is, oh crap, this can't be right. I got 5.29. So that can't be right because that's more than 1. So I got to see what I did wrong. 1.161 for that, for which one? Oh crap. So I did it again. I did a typo and then add everything. What did I not add? Oh crap, that's what I did. Thanks. I uh I copied down the previous answer instead of typing a 1 for this. So this was a very small decimal. I'm just typo heavy today. 1.16. Well, I'll just round that here. 1.17. Thanks for catching that. So now it's the reason why that doesn't make sense right there. All right, here we go. That would explain that. So now it's 1 divided by that. Okay, this is better. 0.8. I'll just round up there 0.86. Awesome. Yes, much appreciated. All right, probability of S2. So this is 1 over 1.17 times E, and that's going to be negative. So the second one, oh, and I calculated that as well, didn't I? 0.14. Actually, let me just type these things in. So that's going to equal, so that's basically the answer to the previous problem times 0.14, and I'll copy the actual value down. Where is it? Right there. I round it to 2, so that's 0.13. Okay, this is looking good. Then probability of state 3, so that's 1 divided by 1.17 times this, which is 0.021. Okay, so I'm starting to see the pattern. So we have uh, this answer times, and where did I put that answer at? There. All right, so I have 0.02 to round there. So the sum I of probability as I to wrap up, that looks pretty good, but I'll add up the actual values in my calculator, see what I get. But that gives me exactly one when I add up the exact values, so that's good. And when we compare the probabilities from before, pretty close, right? So I have 0.86, I have 0.13, and I have 0.02. And I rounded a bit more on the last one. All right, yeah. So what we see, you round it to zero, so to 1.16, you say? Mm. Oh, right here, I got you. I can see. Yeah, but awesome. It worked out. On my calculator, it gave me look, I got 1.16751 for that right there. But give or take on that, it shouldn't make a big difference. So awesome. So looks like it works out. So we see the partition function. We see how it works with the probabilities, and hopefully that's a bit of a help. So the goal is to make an A on my final exam. I just took exam 3, which I don't think I was as prepared for because I was focused so much on a lot of graduate school stuff. I'm getting ready for graduate school. I was working out with research I'll be doing. So I'll be doing the reveal on both channels, by the way, Catherine. Well, I'll be going for graduate school somewhere around in the middle of May. And but I'm already talking with my PI. I'll be researching. I'll talk about that too. Talk about that in the reveal. Talk about what I'll be researching. And but I was focusing on that, trying to get that worked out. A lot of award events and things like that. It's been very busy. So and it took and didn't focus so much on that exam. But I seem to be very good about focusing where I need to focus. So I'm pretty sure I'll do really good on the final. So I'll focus on the final for that class. This class, we had 3 exams. That's what I was focusing on, this exam. For this class, but I think I did all right on. I will see, but I'm sure I did really good on the first 2. And we have exam redo, so even if I did slightly bad, it wasn't so bad. But I could definitely make an A in this class. I could definitely make at least a B in quantum too. I think I can make an A if I do really good on the final. And I'm already making an A in my relativity class and in my building scientific apparatus class. So I just have to write my paper for both of those. So really, for both of those, all I have to do is write a paper, and I'm really good at writing, so sure I'll be fine. That's a bit of an update. So I'll focus on my other work, and just make sure I do well to close out. Then I'll do my reveal and start focusing on graduate school stuff. I will actually take a fun class this semester, which I think will boost my grade point average a little bit. And I always want to study Greek mythology. So I'm gonna study a Greek mythology class over the summer. Maybe I'll do another show or just, I don't know. I'll talk about that a bit, I'm sure. I think we'll be reading the Odyssey. But thank y'all for showing up. I know Galva was here earlier. Not sure if Gal was still here. Always good seeing you, Catherine. And I'll probably take a break, relax, do some offline work, and I'll be back for science hour this evening. And what I'll do is move on to 6.2 in science hour tonight, so you'll be able to see some new content, Catherine. We'll keep it going. So I'll see y'all then. Thanks, Catherine. I appreciate it. Well, you'll have a good evening.